Welcome everyone. I'm Xiaobing, a PhD student of Dr. Zhou. Today, I'm gonna introduce you a paper named Meta-HAR Federated Representation Learning for Human Activity Recognition. In today's presentation, I will talk about 4 parts. The first introduction, I will introduce this human activity recognition test, and also show you the limitation of the federated learning for this task. And also, in the second part, I will introduce you the method proposed in this paper, Meta-HAR, which is a federated representation learning framework, and which is composed of embedding network and personalized classifier, and also experiments on 4 different data sets will show show the superiority of this model compared to other federated algorithms. Also, at last, I will summarize this paper and list some conclusions. First, let's look at the introduction. We can define the human activity recognition as a task of recognizing human activity types based on mobile sensor data, such as accelerometer and a gyroscope. Those 2 sensors are widely used in different higher data sets. And neural networks has the emerging of neural networks has replaced the mutual feature engineering before, and the result, the accuracy has seen great improvement on this task. So today also we talk about neural networks. Now, however, there are some concerns for traditional centralized learning. The biggest one is privacy restrictions on users' data collection. So the federated learning is came to this task. It can utilize the user's sources such as the computational and the storage capability of mobile devices. And also naturally, the federated learning can protect personal information. But there are still 3 main challenges for applying federated learning to this task. The number 1 is heterogeneity in label distribution across users. For different users, they may have different activity sets. And the data sets for each activity can also be very various and personal. And the second one is the heterogeneity in signal distributions of the same activity across different users. The reason is that because users may perform the same action in different styles. And also the third challenge is that the generalization limitation of the federated learning to new user, because the goal of federated learning is to train a single global model. But this one single global model can hardly adopt and generalize to individual users, especially to a new user with their own activity features. So here I will show you an example, the heterogeneity in the signal distribution. Here there is a data set named heterogeneity in human activity recognition, HHAR. This data set collects accelerometer and gyroscope data from 9 users with different smart devices to predict 6 different activities. And the figure 1 show you that the data of one type named stairs down from these data sets. And after reducing the dimension of the features to 2D and using the PCA, you can plot this 2D figure, and you can see that there exists a clear cluster relationship among the different subjects data and also heterogeneity in the signal distributions. This figure is, you may also think it's from last, before the seminar, the paper named the cluster FL. They also use this data set, and they also notice this clustering relationship or the heterogeneity. But here our focus is on how to improve the performance of the model among those heterogeneous. And to overcome the generalization limitations of the federated learning, more and more attentions are brought to personalized federated learning. And the goal here is to customize, personalize a model for each client and boosted by the federated learning. And there are main 4 directions for a personal FL. And federated transfer learning, federated meta learning, federated multitask learning, and federated distillation. I believe last seminar, we have seen some example of this federated distillation. And today, we will see more on this federated meta learning. The federated meta learning is say that we treat each user's model as a separate task. For example, we may have the classification task for each user, but they have different activity sets. They have different labels, and so we treat there as separate tasks. And the shared model here, we also have a server here. So we have shared parts. A shared model here adapts to distribution of the tasks instead of to each individual task. In the federated learning, the server owns a global model, which is to adapt to the distribution of those local data sets. But here we try to learn the distribution of their tasks. So okay, let's say this Meta-HAR method. In the left, the figure 2 shows us an overview of this Meta-HAR framework, which is a distributed learning scheme, very similar to federated learning. It's composed of one server, which is to aim at aggregating the local updates, and clients which owns a local model and their private data. And the local model includes embedding network and a classifier. In the training stage, each participant iteratively updates the embedding network with their local datasets through pairwise similarity loss, and pushed or submits their updated embedding network to the server for the aggregation. And for a new client, we can see the upper right, there is new client here. the new client will download the parameters for this embedding network. And then the activity types are predicted on a device through a two-stage fine-tuning procedure, which I will introduce the details later. And here are some differences between this Meta-HAR and federated learning we should notice. In the Meta-HAR framework, only the embedding network is learned in a federated manner. And the clients, they have their own classifiers. And the client's private data can have a different output activity set and even a different number of activity types. Okay, let's first look at the details of this embedding network. The goal of it is to embed any given input signal, regardless of its activity type, into a fixed length vector. It's another version, I think, another version of word embedding, widely used in neural natural language processing, I think. Okay. Regarding how to convert the time series sensor readings to the feature maps as the inputs here, I will illustrate it in the further data processing section. Here, the embedding network involves combined use of CNN and RNN. The CNN layers are applied to process this sensor signal to model the spatial relevance among these different access of different sensors, as well as the relevance across the sensors. We have two sensors here, and then you use RNN, or in this paper they use the long short-term memory layers to extract the temporal relevance of several time windows and output a fixed length embedding vector. And the training process here, they use a wide sharing semi-network. They use this network to predict whether two signal samples are in the same class or not. So in the training process, there are two samples. There are two inputs. Okay. And they use the pairwise loss. And I will show you more results about this loss function selection. And okay, this pairwise loss, they given the input samples EI, AI, and EJ, AJ, where the EI is the embedding vector and the AI is the label. They first they calculate this cosine distance of these two vectors, and then they compute this pairwise loss based on this cosine distance as the formula, following formula. And where the sigma x is a sigmoid function, and the delta function is that if these two inputs are in the same class, the delta is equal to 1, otherwise it's 0. So you can see here, by minimizing the loss, the cosine similarity between this embedded binding vectors, they will reach the maximum if they are from the same class, and they will reach the minimum if they are from different classes. So also the pairwise loss here, it encourages the clustering of sample embeddings in a real space, bootstraps the training set and makes the embedding network more robust to heterogeneous inputs. It holds the same idea behind this word embedding. After downloading the global parameters for the embedding network, the client will fine-tune the local model in 2 stages. The first stage is fine-tuning the embedding network with the pairwise loss on their private data. And in the stage 2, they jointly fine-tune the output layer parameters together with the embedding network with the cross entropy loss. And here we can see the flexibility of this personalized classifier, because the number of classes is determined by the private data. So they realize this personalization after those 2 stages. And that's all for the measures. Is there any question about the measure? All right. If there are no more questions, like see the experiments. First, they used the 4 different 4 data sets for the experiments. We can see here, let me see. We can see here the row feature, the row features. There are only X, Y, the axis readings from accelerometer and geoscrub. So there are 6 row features for all the data sets. It's very common for this human activity recognition data sets. And each sample here is recorded with unique user ID. And the number of users is ranged from 9 to 48. This the third data set here, merged data set, is produced from the first one and the second one. So we can see here it has 23 users and 7 different activities. And the labels represent 6 or 7 different activities. Compare with the other 3 data sets, the 4th data set, collected data set, has no constraints or control on how the users perform a certain activity. So it's more noisy, and it has more heterogeneity in terms of the signal distribution, mobile devices, and also activity types. And the row readings, I said, only have 6 features, which are not sufficient for this learning. So the data processing needs to convert it to the feature map, feed to this CNN. First, they add an additional input dimension. They add this amplitude for each sensor. For example, the geoscrub they calculate this amplitude and add this new dimension to the raw data. And also they split these time series signals into different into fixed length time windows. And in each window, there are K ratings. Here they use 150, and they extract this frequency components. They apply a Fourier transformation to each axis of each segmented data block. So they get an input area. They stack all the outputs of this transformation, the magnitudes, and their corresponding frequencies, so they can get a tensor of shape k times 2 times 3 plus 1. There, here the 3 denotes these 3 axes, and the 2 is for 2 different sensors, and the F is the length of frequency domain representations. And also they want to mimic the real world. They want to for each user they randomly remove 0 to 2 activities from its local data sets to simulate the scenario where the data sets have non-IED distributions across the different users. And in the last, they split these trained users and test users. They called meta-trained users. These users will participate in this learning process. And the meta-test users is to test the generalization ability of this learning model. Whether for the trained users or for the test users, they all have the train sets and the test set. In the experiment settings, considering the size of the data set, there is one meta test user is random for this HHAR and USC-HAR, these 2 data sets, and the one from the HHAR and the USC-HAR, one from the USC-HAR for this merged data set. And there are 5 test users for the collect data sets. And they compare 5 different models. The central here denotes centralized learning in all data. The Federated average is a classic Federated learning scheme. The feather riptail is applied to first a global initialization of one classification model, and then personalization is achieved by fine-tune this classification model on each user. And the model here CE replace the pairwise loss with the cross entropy loss for the training for training this embedding network. And the experiments also compared 3 different fine-tuning methods. The separate means first you fine-tune the embedding network, then you fix the embedding network and fine-tune the classifier. The merge, it jointly fine-tunes the embedding network and the classifier. And the 2 stages I have introduced before. Okay, let's see some results on HHAR, USC-HAR, and collect data sets. First, let's compare the results of central and Fed average. We can see a great performance degradation, which has been shown in lots of experiments. It adjusts the degeneration brought by non-ID distribution among users, and we can see the Meta-HAR and this Fed reptile. They all outperform this central on this meta test users. This demonstrates that the superior of this personalized model over a single Federated learning global model. And whether for this Fed reptile or this Meta-HAR, as the fine-tuning epochs, the value in this parentheses denotes this fine-tuning epochs. As the fine-tuning epochs increase, their performance is steadily improved. And notice that on this USC hard dataset, there is about 5% performance reduction from the central model to this best personalized models on Meta-train users. Normally, we expect the personalized model perform better in both Meta-train user and Meta-test user. But here, this performance reduction came from that the local data set for each user is too small to personalize this model to get a better accuracy. And if we compare this, compare the Meta-HAR with this Fed reptile, we can see the Meta-HAR shows a slightly better performance. And then let's see more results on the merged data sets. Here is the summary for conclusions I have talked about. Okay, here is the results on the merged dataset. We can see on the Meta-train users, the Meta-HAR model achieves an accuracy of more than 95%, which is greatly outperforms this reptile, which only gives an accuracy of 70%. And on this test users, this Meta-HAR also outperforms this Fed reptile by a great margin. And the performance difference between those two measures is observably greater than the difference on other three data sets. Is because the two data sets merged came from various data collection environments, which leads higher heterogeneity in the signal distribution. So also comparing the Meta-HAR CE using the cross entropy with this Meta-HAR on this on those test users, we can see any questions? Okay, we can see higher performance achieved by this Meta-HAR. This demonstrates that superior generalization ability of this model. And here are some of the results. conclusions for these results. At last, let's see the results for those 3 different fine-tuning methods. And it's very clearly that those 2-stage fine-tuning method is significantly outperform those other 2 epochs on those test users. Here are my conclusions. First, the heterogeneity in signal distribution and activity type distribution across users is readily existing in this human activity recognition datasets. And also, the personalized models can significantly outperform this traditional averaging. And the federated meta-learning shows better generalization ability than the Fed average. And here are some reference. Thanks for listening. Are there any questions?
Hi, Xiaobing.
Mm-hmm.
It was an interesting presentation. Thank you for that. I have a question related to the method. I know that it performs better than the federated learning as well as the federated distillation when it comes to the generalization of the performance.